Hi Rangers, today we're going to be learning how to simplify radical expressions. So Sage purchased a caravan that has a square window with a side length x. If the window has an area of 144 inches squared, write an expression to represent the side length of the window. Then simplify the expression. Well, one thing we know is that it said it was a square window and squares have the same side. So if we draw ourselves a little picture of a square, this is x, that means all of my sides are x. Okay, we know to get the area, it's side times side or length times width. Well, we're multiplying the same number by itself. So if we're given 144 inches squared, all we have to do is take the square root of 144 inches, and that would give me x times x. So the square root of 144 is 12 inches. So each side length of this square window is 12 inches. Now, square roots are examples of radical expressions. So let's write that in. And are often used when solving quadratics. So let's talk a little bit about radicals. So radical expression has a radical sign. If no root index is shown, such as the square root of 49, it is assumed to be a 2 or a square root. So what that means is, if we're looking over here at this picture, if there's no number clearly written right there, it is assumed to be a 2, which means it's a square root. If there's a number there, then it's a different root. So this is known as our root index. Okay, go ahead and let's continue with the picture. This symbol right here, okay, that is known as our radical sign. And the number underneath or the letter underneath is known as the radicand. Okay, so when simplifying a square root, you list the principal or the positive square roots. Okay, so to simplify radical expressions, we can use the product property of square roots shown below. So what this tells us, if I have a number, I can split it up into the square root of a times the square root of b. So we can split it up into two different numbers. So an example, using the fact that the square root of 100 is what? 10. That's something we should know off the top of our head. Rewrite 100 as a product of a perfect square factors to demonstrate. So it already has some of it for us. Let me zoom in a little bit. We're going to break it down. We have the square root of 25 times the square root of 4. 25 times 4 is 100. So we break it down. Square root of 25 times the square root of 4. Then we know the square root of 25 is 5. The square root of 4 is 4. And 5, oh, not 4. 2, there we go. And 5 times 2 is 10. So that's just showing you how the property works and that it is an accurate statement because we got what it equaled up here. Okay, so square root radical expression is simplified when the radicand, that's the number underneath, or the number inside the radical sign has no perfect squares. Factor other than 1. Meaning, there's no way we can break it down into two multiples that are perfect squares. Okay, so an example of something, the square root of 15 is in simplest form because none of the factors of 15 are perfect squares. So if we remember doing our t-charts, 15 is 1 and 15, 3 and 5. None of those numbers are what we consider perfect squares. So therefore, we cannot simplify the square root of 15, and it would stay the square root of 15. But the square root of 12 is not in simplest form because if we look at its factors, we have 1 and 12, 2 and 6, 3 and 4. One of its factors is a perfect square. 4 is a perfect square, therefore this could continue to be simplified in what we call simplifying radicals. Okay, so let's take a second and fill out our perfect square table, focusing on 2 through 10. So 2 squared is 4, so 4 is a perfect squared. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. And 10 squared is 100. All of these numbers that I just wrote right here are perfect squares. So when we're simplifying radicals, we're looking to see if there's a perfect square in it. Okay, so here we go. Complete the table of perfect squares as we did that. Then list the factors of each radicand in 1 through 3 and determine if the radicand expression is simplified. So we're not actually simplifying, we're just determining if it's simplified or if it can't be simplified. So we have 27. So the factors of 27, I'm going to list them in our table because that's what we've been doing. We have 1 and 27. We have 3 and 9. And that would be it. Is there a perfect square? Yes, 9 is a perfect square. So is it simplified? No, this is not simplified. Okay, looking at the next one. We're going to make our t-chart. Remember, we can get this t-chart from the calculator. You would do 38 divided by x in the graph and then Control T to get the table. So our factors of 38 are 1 and 38, 2 and 19. So if I'm looking, none of those numbers are listed are my highlighted yellow perfect squares. So therefore, yes, this is simplified. Okay, looking at 125. So here we go. We have 125. I have 1 and 125, and then 5 and 25. So if I'm looking at this, yes, there's a perfect square right there, 25. So this is not simplified, which means we need to start simplifying it. Okay, so now that we've looked at that, that is the basis of this whole thing. So we need to have these perfect squares with us, and we're going to practice simplifying. So we can use the product property that we talked about above, the A and B, where we split it up into 2 different radicals of square roots, and our knowledge of perfect square factors to simplify radical expressions with the steps below. So here's our steps. Okay, 1, we're going to find the largest perfect square factor in the radicand. Okay, so basically what we did just a second ago. Okay, but it has to be the largest. Then we're going to rewrite the radicand as a product using the perfect square factor and the product property. Okay, and then we're going to take the square root of any perfect square. Okay, so I'm showing you what that looks like above here. We have the square root of 27. So we said 9 was a perfect square, so 9 times 3 is 27. So we're going to rewrite this as 9 times 3. Then that property tells us we can split it up into 2 separate radicals. The square root of 9 is 3. 3 is not a perfect squared, so it stays inside the radical, and this would be it simplifying. Okay, number 2 was already simplified, but number 3 wasn't. So this is what it would look like. We have 25 times 5. So we have 125, we have 25 times 5. Then I break it up, 25 times the square root of 5. Well, we know the square root of 25 is 5, so we're left with 5 rad 5. Okay, so another example before we start doing it ourselves. We have 24. So we want to simplify it. So what we will do is we will list the perfect squares that go into it. So we have 24. We got 1, 24, 2, and 12, 3, and 8, 4, and 6. So this already gives us a hint that 6 is one of them. So that perfect square would be 4, and 4 is perfect. So we're going to write a 4 here. Then we split it up into two different radicals. So that's the square root of 4 times the square root of 6. Square root of 4 is 2. So we get 2 rad 6 as our answer. Okay. So we're going to do these together. So here we go. We have the square root of 48. So let's see what we have. Okay. So 48. I'm going to show you again, just in case you forgot, how to use the calculator. So we're going to go to our calculator screen. We're going to add a graph. We're going to do 48 divided by x. Enter. Control T. Control T. Here's all our factors, so I'm going to put my notes on top. Okay, so we have 1 and 48, 2 and 24, 3, 16, 4, 12, and then 6 and 8. So going back to our notes, okay, now, most of us would see 4, and yes, 4 is a perfect square, but we want the largest perfect square, and the largest perfect square we have is 16. So we're going to use 16. If we use 4, we would not have simplified it all the way, and our answer would not be correct. So the largest perfect square, which is 16. So we break it down to 16 times 3, the square root of 16, times the square root of 3. The square root of 16 is 4 times the square root of 3. So our answer would be 4 rad 3, or 4 square root of 3. Okay, looking at the next one, we have 300. Okay, so I'm going to go back to our calculator. We're going to add a new graph, 300 divided by x, Control T. So here we go. Whoops, not what I wanted to do. So here we go. We have 1 times 300, 2 times 150, 3 times 100, 4 times 75, 5 and 60, 6 and 50, and we have 10 and 30. Last but not least, oh no, we have a couple more. 12 and 15. Oh, nope, that's it. 12 and 15. Oh, nope, 15 and 20. Sorry, 12 and 25. There we go. 15 and 20. This one has a lot. Now, did we have to list all of these? No. Once you see a perfect square or the largest perfect squared, you can stop listing them. So in this one, the largest perfect squared is 100. So we're going to break this down to the square root of 100 times 3. Square root of 100 times the square root of 3. Square root of 100 is 10. Square root of 3 stays there. Okay, now this one seems a little bit different, but it's not. It's exactly the same. Okay, this 2 is just going to hang out until the very end. So it's just going to tag along. So 45. Okay, so 45, we're going to go over here, discard my changes. This time I'm not going to list them. Okay, we're going to work on getting faster at this and understanding what we're looking for. So again, we're looking for the largest perfect square that goes into 45. So we have 1 and 45. Neither one of those are perfect squares. Okay, we have 3 and 15. Neither one of those is perfect squares. We have 5 and 9. 9 is a perfect square, and that is the largest number that goes into both of them. So that is our combo, 5 and 9. So I'm just going to write it here again because 9 is our perfect square. So this 2 just tags along, and it's being multiplied. So we have 9 times 5. Then we have the square root of 9 times the square root of 5. Well, the square root of 9 is 3 times the square root of 5. And then I have this 2 that's being multiplied. So I can multiply the numbers on the outside together. 2 times 3. So we get 6 square root of 5. Now, the nice thing about this is you can always check your answer with the calculator. So I'm going to type in 2 square root of 45 and then 6 square root of 5 and show you that we get the same decimal. So to check your work, you go to the calculator screen. We have 2 square root of 45. It gives us 13.4164. If I type in 6 square root of 5, notice I get the exact same decimal. So that's how you can check your work. But when we want it simplified, we don't want decimals. So it's important to know how to simplify the radicals. Okay, it's going to help us when we're talking about quadratic formulas coming up very soon. So we have 3 more examples that we're going to go through, and then you can summarize what you learned today. So Joe and Audrey believe that their expressions below are already in simplest form. Circle the name of the student who is correct and simplify the expression of the other student who is incorrect. So we have Joe has 3 square root of 153, and Audrey has 4 times the square root of 139. So what we need to do is we need to pull up our table and see if there's a perfect square that goes into the radicands, the numbers under the radical. So I'm going to start with Joe first. So I'm going to do 153 divided by x in my graph. 153 divided by x, Control T. Okay, so I'm going to look. I have 1 and 153. Neither one of those are perfect. I have 2, nope, that gives me a decimal, skip the decimal. 3 and 51, neither of those are perfect. I have lots of decimals. I have 9 and 17. We know 9 is a perfect square, so that one is not simplified. So Joe's needs to be simplified some more. Okay, so Joe's can be broken down into 9 times 17, which is 3 times the square root of 9 times the square root of 17, which is 3 times 3 times the square root of 17. 3 times 3 is 9, square root of 17. So that would be Joe's completely simplified. So he did not simplify it correctly. He left it and he would have got it wrong. Now let's check Audrey. So we're going to type in 139. Okay, so I'm going to go and get me a new graph. Control T to get my table. Okay, so if I'm looking, 139 is not perfect, and then I'm not seeing any other whole numbers, so it looks like hers is completely simplified. So Audrey was correct, so we need to make sure we circled hers, and we solved the one that was incorrect. So perfect, done. Okay, Tamika is baking cupcakes. The square of the pot holder she is using has an area of 40 square inches. Write an expression to represent one side length of her pot holder and simplify. So this is like what we started with in the beginning. So remember, if it's a square, all the sides are the same. So x times x gives us our area. Well, we know the area is 40, so we need to take the square root of the area to see what the side length is for one side. So going to our calculator, Again, we're looking for the biggest perfect square that goes into 40. So I have 1 and 40, 2 and 20. None of those are perfect squares yet. 4 and 10. Winner, winner, chicken dinner. 4 is our largest perfect square. So I break this down to the square root of 4 times 10. Then I have the square root of 4 times the square root of 10. And the square root of 4 is 2. The square root of 10 is not perfect, so we leave it there. And it is inches. Okay, moving on to the last one, and then you can summarize. Ulysses simplified the square root of 72 and got 3 rad 8, as shown below. Explain why his answer is not correct and give the correct answer in simplified form. Well, let's see what he did. He said the square root of 72 breaks down to 9 and 8. The square root of 9 is 3, and then he left the square root of 8. But we know that the square root of 8 can be broken down into the square root of 4 times the square root of 2. Well, the square root of 4 times the square root of 2 is 2 rad 2. So we need to take this and replace it here. Okay, so that leaves us with 3 times 2 square root of 2, which is 6 square root of 2. Okay, now if you lost what I did, that's fine. I'll show you how you could have simplified it just by starting from the beginning. Okay, but that's just to show you how you can make sure that if you pick the wrong perfect square root, you check the other radical to see. Now, what we could have done is broken it into 2 different ones right here. So let's look at 72. divided by x. Control T for our table. Okay, so if we would have started right here, okay, instead of using 9 and 8 like Ulysses did, we could have used 2 and 36. 2 and 36. So this is a different way to do it. So we break it down to the 36 times the square root of 2, which is the square root of 36 times the square root of 2, which is square root of 36 is 6. Square root of 2 stays that, and that's what we got in the other one. Okay, so what I would like you to do is summarize what you learned in this video. If you have any questions, please make sure you ask your teacher. Have a great